In our previous lectures, we have already discussed two different levels of material structure, such as atomic level as well as crystalline structure. It is time to move to the larger scales, and today we will discuss the microstructure of material. Very important level of structure which defines very many kind of material properties. So the best way, I believe, to illustrate and to provide some definitions and illustrate this idea is to come back to the mechanism of the material plastic deformation in metals, let's say. And again, remind you that the plastic deformation in metals occurs owing to the motion, owing to the slip of different type of dislocations. In this screen, so we are using edge dislocation as the example. So you can see that indeed, in this case, only the atoms, bonds at the center of dislocation break and restore to allow the dislocation to move. So, and because of that, of course, the mechanical properties such as sigma yield, tensile strengths are much less as compared to the case if we expect that atomic bonds will break along the whole plane, along the whole cross-section of our material. So, and again, if we have a single crystal, an example of single crystal you can see on this screen. So we do have the slip and the motion of dislocation, and when they reach actually the surface of our sample, we do have the result of these plastic deformations, and all these parameters can be calculated, and they define again, so they define the different type of material properties. It's very easy to understand. In order to make material stronger, somehow we have to hinder the slip or the motion of these dislocations, for example, edge dislocation. Before we talk typically about two atoms, when we consider the atomic level of structure, or we talk about the single crystals, so when we discuss the crystal systems as well as material properties which are related to the crystal level of structure. But you know that in reality, many of materials, they are polycrystalline materials. So it means that these materials involve or consist of very many this kind of single crystals. And if you do have many kind of single crystals, and you can imagine that inside each crystal, again, the slip occurs along, as we know now, the direction with the highest atomic density in general. So when these dislocations, they reach the boundary of each crystal, so in principle, the direction of dislocation motion should be changed. And as the result, so it's some kind of hindering of motion of dislocation takes place. So from this example, from this image, you can see that in principle, the size of grains, which typically is on the order of microns, 100 microns, 50 microns, yeah, something like that, they should influence the dislocation motion. As the result, they should influence material properties. So that's the way how we can to understand that such very important parameters such as size of grain inside your material is a microstructural parameter of your material which defines the mechanical property of this material, for example. So, for this reason, let's see how we can make harder, how we can hinder the material, the motion or slip of this dislocation. And as it comes from the previous our discussion, just for example, we can make our grains smaller. In this case, we have much more, let's say, the grain boundaries. On the grain boundaries, we will have the loss of energy because dislocation should change the direction of their motion. As the result, we will make our material much more stronger. So that's different strategies how to make material stronger, and strategies for material strengthening, and reduction of grain size is one of the main approach. And let's talk about this very important parameter such as the grain size. How we can change the grain size and how the mechanical property depends on the grain size. First of all, we can change the grain size by applying different type of manufacturing conditions or synthesis conditions or fabrication production conditions for these materials. And so we will be covered in our lecture, which is related, let's say, to the phase transformations, for example. But even in this lecture, I will show you several approaches how we can control the grain size of the material. So this slide, let's say, demonstrate you how sigma yield, very important mechanical property of the material, depends on its grain size. This so-called the whole patch equation describes the dependence of the yield strength as a function of average grain size, and you can see on the graph that decreasing of grain size leads to increase of the sigma yield. And sigma yield, please put your attention that this equation was obtained based on the statistical treatment of very many experimental data for metals, and so it means in some sense it's not a theoretical formula obtained based on the analysis of some model. On the other hand, also please pay your attention that this type of dependence does not work for the nanomaterials. It's a separate story to discuss how actually mechanical property of nanomaterials depends on their size. But for extremely wide range of materials, metals and alloys, where actually the main mechanism of the material failure is due to the slip of different type of dislocations. So indeed, this formula describes this dependence pretty nicely. So now we know smaller microstructure, finer microstructure of your grains, you have to expect higher mechanical property of this material. So now, how we can control the grain size? It's very, very important. But before we go to that, the other strategy how we can make our material harder is so-called strain hardening. And this approach is extremely interesting as for me. So again, we know that the dislocations, somehow they define their motion, their slip, defines the mechanical property of material. And if we do have the density of dislocation, and actually dislocation size and dislocation also can be attributed to the microstructure of the material. So if the density of these dislocations less than some critical, then of course increase the density of dislocation leads to the decrease of the material mechanical property for sure. However, at some critical point, and you can imagine that the number of dislocation per volume appears to be so high that dislocations start to interact with each other. In this case, this interaction somehow hinders the motion of this dislocation, which leads to the material hardening. And this approach has a name, it's strain hardening. How to reach strain hardening? For example, one of the approach is cold work, as you know. You have to apply some strain to your material, which leads simultaneously to the decrease of grain size and to increase of the dislocation density. Altogether should lead to significant increase of sigma yield and tensile strength. On this screen, you can see different type of operation, including forging, rolling, drawing, extrusion, which leads to the cold work and results in changing of sample cross-section, and on the microstructure level, as I mentioned, results in the decrease of grain size and increase of dislocation density. And again, so you can go and use different type of diagnostics, including transmission electron microscopy or scanning electron microscopy. About this technique we will talk later in our lectures, and even calculate the density, the density of dislocation per volume of your material as a function of applied of cold work. It's not bad to have these general ideas that so carefully prepare sample. So when we try to avoid dislocation in them, so in this case we have density of the dislocation in the order of the 10 in the power 5 dislocation per millimeter cube. In the heavily deformed sample, when we apply the huge cold work, so their density can be, let's say, as high as 10 in the power 10 number of dislocation per millimeter cube. So why it's so important, why we again discuss this issue in relation to the controlling of the grain size, just for the reason that when we applied different times the cold work operation to our material, we will see that on the stress strain diagram that indeed it leads to significant increase of sigma y, as you can see on this screen, significant increase of TC on this screen, and we can apply this kind of drawing, for example, for wires for 5, 10, and whatever number of times. At the very bottom, so we significantly increase strength, but significantly decrease ductility. And it's not easy to work with this material, of course, while it's extremely strong. And so the next step, an important step for us, is a annealing step, which we typically use after the cold work in order to reach the grain size and the concentration of the dislocation exactly which correspond to the desired number of the sigma yield, tensile strength, and ductility of this material. So let's talk a little bit about the annealing process, which actually very interesting because different, let's say, driving forces play roles on different stage of the annealing. So, and annealing in general involves 3 different stages: recovery, recrystallization, and grain growth. So what is recovery in general, and so how it works here? So recovery is the very first stage of annealing after cold work, and on this stage we cannot see even dramatic change of the grain size. However, what we see that strain which we introduce inside our material slightly decrease. This conclusion can be obtained by making X-ray diffraction analysis, and we will discuss it on the next lecture. And so, however, during this first stage, the decrease of sigma yield or increase of ductility is relatively small. But this is important stage. However, the next stage actually is so-called recrystallization. And this is very interesting case for me from the standpoint of the microstructure transformation stage. So what we can see, I think it's better to see on the to understand this on the example shown on the screen now. So we do have initial, on the very left side, initial microstructure image of brass after 33% of cold work. We can see a huge grains, and because it was 33% of cold work, we can imagine that a lot of strain was introduced inside this material, and a lot of dislocations now we could find in this material. So now let's put this brass at temperature 580 degrees. And assume that we have a microscope which allows us in situ observe the microstructure transformation which we can see with our material. And this is really amazing. In 3 seconds, only 3 seconds and 580 C, we could see that instead of the large grains of brass after cold work, the nucleation, the formation of extremely small grains, exactly same composition of the brass, start to form in the volume of the big grains. And in 4 seconds, can you see it? On the 4 seconds, the half of the large grains, they already transform to the small one. In 8 seconds, we have complete recrystallization. Instead of big grains after cold work, we have very many small grains, 8 seconds, 580 C. Unusual, indeed unusual, because in general we know the larger the grains, the smaller the grain boundaries, and in general should be smaller the energy of the whole system. And because of that, we know that in typical mechanism of grain growth just based on the growing of the small grains to large grains occurs due to this type of mechanism, because the system wants to be on the under the lowest energy conditions. And as again I mentioned, that grain boundaries typically they do have extremely high energy, and larger grain size, low energy of the system. So here we could see during recrystallization absolutely opposite, if you want, transformation sequence. From large grains, small grains formed. And because in this case the driving force of the process is reduction of total energy of the system during to release of the energy which we introduced inside the metal during cold work through recrystallization and formation of the new grains, smaller grains, but without this kind of deformations and without this kind of dislocations which we introduce during the cold work. This is the recrystallization stage. So next, when we continue the heat treatment of our material, annealing of material, these grains start to grow owing to the very well-known mechanism or driving force indeed. So in order to decrease the grain boundaries surface, and we can see that in 15 minutes the grains of brass, so they became, let's say, almost comparable with the initial size of grains of the cold work. And so we can stop this process on any stages and obtain material with the desired grain size which correspond to the desired mechanical property of this material, for example, sigma yield, TS, ductility, and so on and so far. So this example, as for me, very nicely demonstrate how actually so we can control the grain size of our material, specifically of metals and alloys, and by controlling the grain size, how we can control the mechanical property of this material. I wanted to say that grain growth, and this is the last stage of the annealing, occurs again owing the driving force to decrease system energy by decreasing the size or surface, grain boundary surface. And so in order to control it more precisely, you have to know the kinetics of grain growth. And typically, and this screen demonstrates this, typically, so one can find this kind of equation, kinetic equation, dependence of the current size of grains as a function of time. So, so knowing this dependence from different books, or you can obtain this dependence experimentally, you can control precisely the time and temperature of annealing, of the grain growth stage of annealing, and in this case you can obtain again material with the desired grain size and mechanical property. Again, coming back to the strengthening by reduction of grain size. So controlling the size, we're controlling sigma yield, sigma tensile strength, and now you have a general idea how the microstructure and such important parameter, microstructure parameter as the grain size dictates or can be controlled, and how it's influenced such important material mechanical property such as sigma yield and sigma tensile strength. And also this type of explanation so helps us to show at least to give you very nice one example that actually the all level of material structure, so specifically micro level of material structure, can be controlled by the changing of the operational fabrication condition of this material. Thank you very much for your attention.